All right, then let's move on. We started in the last class with the Metallocenes, and I told you that the first Metallocene which was discovered was the ferrocene. And in the ferrocene, we had iron sandwiched by two cyclopentadienyl anions, which are aromatic. Now we can of course ask the question: are cyclopentadienyl anions the only anions that we could use in order to make metallocenes? Could we also use other cyclic systems in order to do an analogous chemistry? So one obvious choice would of course be the benzene. So the benzene has one more carbon atom in comparison to the cyclopentadiene, and it's also aromatic. So in a Metallocene complex, benzene would be a so-called hepta or hexahapto ligand, because all carbon atoms would be used in its interactions with the metal. So we said that in the case of the ferrocene, the particularly high stability of the ferrocene results from the fact that the complex obeys the 18 electron rule. So we said that the cyclopentadienyl ligand contributes 6 electrons each, and that makes 12. And if we consider iron in the oxidation state 2+, then that gives 18 electrons. So now we can again ask, what metal would we need to use in order to make a sandwich complex using benzene as the ligand? So if you wanted to obey the 18 electron rule, what metal would you suggest?
So like as the sandwich.
Sorry?
So like having one on top and one on the bottom. And then
Yeah, so if we assume that we had two benzene rings and sandwich metal, which metal would we need to use in order to create an 18 electron complex which may be stable? So if you wanted to synthesize metallocene with benzene, which metal would you choose so that you most likely create a stable complex? Virtual students are also invited to answer.
Could you use a group 8 metal with like a +2 oxidation state?
Yeah, but you also have to think about the oxidation state of the metal. Okay, in the case of the cyclopentadienyl ligands, we said we have 6 electrons when our cyclopentadienyl ligand is an anion. Okay, we have a 1- charge. So therefore, the iron need to be in the oxidation state +2. So in this case, we have a benzene ligand. So this benzene ligand already has 6 electrons when the benzene is neutral. Okay, so if we wanted to create a neutral complex, then what would the oxidation state of the metal need to be? 0, correct. Okay.
So 6 metal?
Correct, a group 6 metal. And well, there are the chromium, the molybdenum, and the tungsten. And well, the most simple choice would be probably the chromium. And indeed, we can make a stable sandwich complex if we use chromium in what is called a bis-benzene chromium 0 complex. Okay, we can verify that we have 18 electrons in this case, so the chromium has 6. Then the ligands have 6 pi electrons each. So because we have 2 ligands, we have 12 ligands, so 12 electrons overall, and 6 plus 12, that gives overall 18. Okay, now let's go into the other direction. Let's do not make the ring larger in comparison to the cyclopentadienyl ligand. Let's make it smaller. So when we make it one carbon atom smaller, we arrive at a cyclic pi system, which is called the cyclobutadiene. And in a sandwich complex, the cyclobutadiene would act as a hepta 4 or tetrahepto ligand. So there's a significant difference in comparison to the other two ligands. So the other two ligands were aromatic. They had 4 n plus 2s equal to 6 electrons, and in this case would be just 1. But that doesn't apply to the cyclobutadiene, which is anti-aromatic because it has 4 n electrons. In this case, n would be equal to 1, and 4 times 1, well, that's 4. And that would make sense because cyclobutadiene has 2 carbon-carbon double bonds containing 4 pi electrons. All right. So how can we actually see this anti-aromaticity? We can again see this when we construct the molecular orbitals, the pi molecular orbitals. So in this case, we have to consider 4 pz electrons that stand perpendicular to the plane of the molecule. So therefore, we would expect 4 molecular orbitals resulting from the combination of these 4 pz orbitals. So they're actually shown here. So this one here is completely bonding and has no node. So these two here, they have one node here and here, and they are non-bonding. You can easily see that the bonding and the anti-bonding interactions in the molecular orbital exactly cancel out. So it's exactly non-bonding. So we have bonding interactions between these two and these two PZs, but you see we have anti-bonding interactions between these two and these two. And from geometric inspection, we can easily see that they cancel out. And well, for this one here, it's exactly the same. It's just that this one basically is a 90-degree rotation of this one. We have now the bonding interactions between these two and these two, and the anti-bonding interaction between these two and these two. Okay, last but not least, we have an anti-bonding molecular orbital, which is this one here. So this has 2 nodes. We can easily see that it's anti-bonding because there are only anti-bonding interactions between the lobes of the orbitals. So now in the cyclobutadiene, we have 4 electrons. So for that reason, we have to fill this bonding molecular orbital here and these 2 non-bonding ones. So you see that in contrast to the cyclopentadienyl fragment, or the cyclopentadienyl anion, and the benzene, it's not that all bonding molecular orbitals are full and all anti-bonding molecular orbitals are empty. This is actually a result of the stability of the aromatic system. Here we have our bonding molecular orbitals being filled, but 2 non-bonding molecular orbitals have to be half filled. So for that reason, this pi system is not aromatic. It's called anti-aromatic and has a smaller stability. In addition, of course, you have the ring strain within the cyclobutadiene, because of which the cyclobutadiene molecule is not a stable molecule at ambient conditions. So at the first glance, you may also think that the cyclobutadiene molecule is a square planar molecule, because you may think that the pi electrons are actually delocalized because you can draw 2 resonance structures for the cyclobutadiene molecule, and the common interpretation of resonance structures is that the real structure lies in between the 2 resonance structures. Okay, and that would then result in an exactly square planar molecule. However, the cyclopentadienyl molecule is not square planar. We have again a Yarn-Teller distortion due to partially occupied degenerate orbitals that leads to a distortion, and in this case, a localization of the pi electrons. Okay? So we can write the cyclopentadienyl molecule either this way, or we can also localize the pi electrons here and the single bonds here. That, however, would only be a 90-degree rotation of this molecule. So now, why would the distorted molecule with localized pi bonds and two short carbon-carbon bonds and two long carbon-carbon bonds energetically be favorable? The answer is that the formerly non-bonding electrons can be stabilized and become bonding electrons because of the distortion. So how can we understand this? We can start out from this picture here. So this is our first non-bonding molecular orbital. This one is our second one. Okay, in order to fulfill Hund's rule, we would fill both electrons spin up in the two different orbitals. So one goes in the first orbital and the other one goes into the second orbital. All right, so now if we realize this structure here, then that means that when we start out from this orbital, we squeeze the interbonding orbitals closer together, and the bonding orbitals here, the bonding interactions, weaken because the orbitals are further apart. So this means that this formerly non-bonding orbital now becomes weakly interbonding. So with this orbital here, the contrary happens. We see that if we distort the molecule, then the bonding interactions here and here strengthen because the respective lobes that create the bonding overlap come closer together, whereas the lobes that create the interbonding interactions are now further apart, and therefore the interbonding interactions weaken, and that results overall in a bonding situation for this orbital. So now we can take these two electrons and fill them into the bonding molecular orbital. Therefore, we have actually net stabilization of these two electrons, explaining the distortion. So of course, like I said before, we could also distort in the other direction, but the molecule that we create would be only a 90-degree rotation from this one, so we could superimpose the two molecules by 90-degree rotation, meaning that they're actually identical. Okay, but we can, of course, also making the exercise of creating a molecular orbit also for this case. So for this molecule here, well, this orbital here would become interbonding because we bring the interbonding lobes closer together, and we will have the bonding lobes further apart, while this one here will become bonding because now the bonding lobes here are closer together and the interbonding lobes are further apart. Okay, we can again fill the formerly non-bonding electrons into the bonding molecular orbital. Okay, this is another example of a Yarn-Teller distortion, which always happens when we have partially filled degenerate orbitals. All right, so now what about the cyclopentadienyl molecule as a ligand? So sandwich complex with cyclopentadienyl itself is actually not known, but the derivatives are known. So this molecule here with cyclopentadienyl having 4 phenyl substituents here and here is known as a stable structure. So in this case, interestingly, we observe that our cyclopentadienyl ring is exactly square planar. This is also observed for other complexes with cyclopentadienyl as a tetrahaptoligand. So for instance, in this molecule, where we have cyclopentadienyl attached to iron, and we have here in this complex 3 CO ligands. In addition, we observe that the cyclopentadienyl ligand is square planar. So now, of course, the question is, how could we explain this? One way to explain this is to argue that, well, we consider these ligands not as neutral ligands, but as anionic ligands. And then formally, we have an aromatic system because our the number of pi electrons is not 4, but 6. So in this case, we would have a nickel 4 plus, Cb 2 minus 2. And in this case, we would have an Fe plus Cb 2 minus. Of course, this Q is a little questionable because when we fill additional electrons into our non-bonding orbitals, we do arrive at 6 electrons. But of course, in contrast to really aromatic system, not all electrons are in bonding molecular orbitals. So we add actually non-bonding electrons, which does not contribute to stability. However, we could also take an opposite view and say, well, when we have actually only if we had only 2 electrons in our pi system, then we would formally arrive at aromaticity, because in this case, n would be 0, and 4 times 0 plus 2 would be 2, and that would also be an appropriate number for aromaticity. And then also we would have electrons only in bonding molecular orbitals. However, then we would have to assume that our ligand is not an anionic ligand, but a cationic ligand, which is a very unusual perspective. And we would have to assume that our nickel and our iron here would be negative oxidation states, which is also unusual. Okay, however, it's not impossible, in particular, when the ligands are very good pi acceptors. So for instance, here we have actually 3 carbonyl ligands, which are very good pi acceptors that actually can stabilize negative oxidation states. Which would argue that a negative oxidation state for the metal would actually not be all that unplausible. All right? But these are just superficial views on the bonding in these compounds. Now, anyhow, but they help to rationalize why the cyclopentadienyl ligand in this case is exactly square planar, not distorted. All right. So now let's go to a very large cyclic pi system, the cyclooctatetraene, also abbreviated COT. So this is also not an aromatic ligand, it's anti-aromatic because we have 4 n electrons. In this case, n is equal to 2, so we have 8 pi electrons because we have 1, 2, 3, 4 for double bonds. Because anti-aromaticity The cyclooctatetraene is not planar. It has actually this boat-like shape here. However, when it acts as a octahapto ligand, then it can also become exactly planar. However, ligands with the cyclooctatetraene ligand as heptade ligand is only known for metals that are very large. Yeah, for example, you can make uranocene with uranium as a metal and 2 cyclooctatetraene ligands. So this is possible because the uranium has orbitals large enough in order to effectively overlap with the p orbitals of the carbon atoms in the cyclooctatetraene ligand. All right, so now again we can ask for explanations. Why do we have here planarity while we do not have planarity in the free ligand? Again, superficial explanation would be that we consider our ligand is an anionic ligand, and then our uranium would be in a positive oxidation state. That would make the cyclooctatetraene formally aromatic. If you add 2 electrons to the neutral ligand and make a cot 2-. The uranium would, in this case, then be in the oxidation state +4. Okay, now the cyclooctatetraene can also bind in other ways. Just to make this complete, can also bind in hepta-2 and hepta-4 fashion, utilizing also in hepta-6 mode, utilizing only 2, 4, or 6 pi electrons. The 18 electron rule holds in the most cases. So here's just a couple of examples. So here we have a complex with cyclooctatetraene in hepta-4 binding mode. So we use these 4 pi electrons here to bind to the ruthenium, and in this complex here we would have 3 additional carbonyl ligands. Could verify that the 18 electron rule holds by electron counting. The ruthenium has 8 electrons. Okay, let's apply the neutral atom method. So the carbonyl ligands contribute 2 each. So 8 plus 4, that gives, 8 plus 6, so that gives 14, right? So we need 4 to make 18, okay? And that explains why 4 of pi electrons of the cyclooctatetraene are being utilized, okay? So we could also utilize the other 2 if we added another ruthenium tricarbonyl fragment to the other end of the cyclooctatetraene, and that's also no. Okay, then let us start a new subchapter. We still stay with the organometallic. We stay with the organometallic chemistry, but move now from the Metallocenes to the carbonyls. So carbonyl complexes are another important class of organometallic compounds for a number of reasons. So first of all, they have a very diverse coordination chemistry. There's a great structural viability in carbonyl complexes, and there are reasons for that, and we are discussing these reasons in a moment. So in addition to that, they're useful as starting materials for other coordination compounds, just because the carbon monoxide ligand is a gas. So one can drive a substitution reaction very easily by providing the new ligand and at the same time purging the reaction vessel. Then any CO molecule which is formed, okay, goes in the gas phase and can be purged out from the reaction system fairly easily, and then drives the reaction just to the right side. So another reason is that the substitution happens very facile, so the carbonyl ligand in many cases binds strong enough to provide a stable molecule, but the binding is also weak enough so that you can fairly easily substitute it by another ligand. Another interesting feature is that CO is a C1 unit, so one can use this for organic synthesis and use carbonyls as intermediates in the synthesis of more complex molecule in which you add one carbon atom to an existing molecule. So last but not least, as I mentioned already before, carbonyls can stabilize metal in low oxidation numbers. We can even achieve highly negative oxidation numbers of metals, which is very unusual for metals under normal circumstances. All right, so now let's approach the chemistry of metal carbonyls by briefly reviewing the molecular orbital diagram of CO. So much of the structural diversity of metal carbonyls basically is a result of the bonding in the carbonyl molecule itself. So we have here our highest occupied molecular orbital, and we have previously seen that we can associate this highest occupied molecular orbital here with the electron lone pair at the carbon. So the electron density of this HOMO is primarily at the carbon, because of which the carbon is the reactive end, not the oxygen. So this is in some ways counterintuitive because the oxygen is more electronegative. So usually, electronegative atoms have a higher affinity to electropositive ones. So metals are typically electropositive. So at first glance, one would expect that the oxygen here is the reactive end, but no, it's the carbon, and that's because the HOMO has its electron density primarily at the carbon. Okay? So now, in addition to that, we have here our LUMOs. So the energy of these LUMOs is low enough so that the carbon monoxide as a ligand can relatively easily accept electrons from the metal. Therefore, it can easily act as electron acceptor. But also the bonding pi electrons here are energetically high enough so that they can be utilized for bonding in certain circumstances. Even these electrons here, which could be associated with the other electron lone pair here, the oxygen, can under certain circumstances be utilized, but this is pretty rare because the energy of these electrons is already pretty low, but examples for carbonyls in which the electron lone pair and the oxygen is being utilized are also known. Okay, with this in mind, let's think about the possible binding modes for the carbonyl ligand. So let's first think about sigma bonding interactions. So in the most simple case, the carbonyl ligand would utilize its electron lone pair at the carbon in the valence bond picture, or its highest occupied molecular orbital in the O picture, to make a sigma bond with the metal. Okay, so it would bind terminally at the metal. So not only the binding to a single metal is known, we can also bind to different metals when our complex has a metal-metal bond. In this case, our 2 electrons are being shared between 2 metals. So even the sharing of 3 metals is being known. So this is called the Mu bridged binding, and this is a Mu3 bridged binding, because here 3 metal atoms are bridged, while here there are only 2. All right, so there's even the possibility that of unequal sharing. So if you have 2 different metals, for instance, the carbonyl ligand may have a higher affinity for one in comparison to the other. That would then result in unequal distances between the carbon and metal atom number 1 and the carbon metal number 2. So this is called semi-bridging because one bridge is weaker than the other. Okay, so in all cases, the CO acts as a 2 electron donor, okay, but the 2 electrons may be shared between more than 2 atoms. Only in the first case, it's being shared between 2 atoms, 1 carbon and 1 metal. In all the other cases, it's being shared by the carbon in 2 or more metals. Okay, so what else is possible? We can also have sigma binding interactions between the bonding pi electrons within the carbonyl and the metal. But this is only possible if we have already established the sigma bonding interaction between the electron lone pair here at the carbon and the metal. That is because the electron pair represents the most energetic electrons, because the HOMO is the highest energy orbital. But if it's already utilized, then also the pi electrons, the bonding pi electrons within the CO ligand, can be used for bonding interaction with another metal. Okay, so bonding pi electrons would be donated in this case into a second metal, and that orbital overlap also occur in a sigma fashion. Okay, so again, these electrons can not only be donated into the orbitals of one metal, but we can also have 2, for instance. And in this case, we have a Mu3 hepta-2 binding mode. We say hepta-2 because we have both the carbon and the oxygen involved, and we call it Mu3 because, again, 3 metals are being involved. So in this case, we have Mu2 hepta-2 bonding situation. It's again hepta-2 because both the carbon and the oxygen are being involved. It's Mu2 in this case because 2 metals are involved. So in the former case, our CO ligand would act as a 4 electron donor. Okay, it would utilize only one of the 2 pi bonds to create the bonding interactions, whereas here it would be a 6 electron donor. It would use both pi bonds to make bonding interactions. So the first pi bond would be used to make bonding interactions with the first metal. The second pi bond here would be used to make bonding interactions with the second metal. Of course, an additional 2 electrons would be used in order to make the sigma interactions between the electron lone pair here at the carbon and the metal. So therefore, overall, we utilize 4 electrons here, but 6 electrons over there. All right, so we can even have a third case. So this is called the Mu3 hepta-2 binding mode, where we have the carbonyl ligand is a 4-electron donor. In this case, the electron lone pair here at the carbon would be shared between the two metals, and then 2 pi electrons would be donated into the metal. Okay, so last but not least, we can also have what is called an isocarbonate. So in certain geometric circumstances, the electron lone pair at the oxygen atom can also be utilized in addition to the electron pair at the carbon. In this case, the carbon ligand acts as a bridging ligand, overall donating 4 electrons, but this case is rare because it requires special geometric circumstances. The energy of the electron lone pair here at the oxygen is so low so that they cannot be easily utilized. Okay, now in addition to sigma bonding, we can also make pi bonding, and the most common way of providing pi bonding is end-on binding with pi interactions. So in this case, a full metal d orbital interacts with one of the 2 empty pi star orbitals. So this creates a very effective orbital overlap for 2 reasons. First, the orientation of the lobes of the orbitals is right. But secondly, due to the relatively high electronegativity difference between the carbon and the oxygen, the lobe of the pi, or the lobes located at the carbon atom, are much larger than the lobes at the oxygen atom. Remember always, interbonding orbitals are primarily located at the electropositive atom. Okay, so this rule applies here. The carbon atom is more positive than the oxygen atom. Therefore, the interbonding pi star orbital is primarily located at the carbon, not the oxygen. Okay. But that's not the only possibility. The second possibility is that we bind side-on to the carbonyl ligand. Okay. From this picture here, it's clear that also the side-on overlap is a pi overlap, whereby now one lobe of the full metal d orbital overlaps with an empty lobe at the carbon, and the other lobe of the metal d orbital overlaps with a lobe here at the oxygen. However, this is not as effective, okay, because these lobes are unequally large. Okay, so therefore there's uneven overlap, and that does not lead to that stable bonding situation. Okay, so now we have considered both the possible sigma as well as the pi interaction. Now, the sigma bonding interactions and the pi bonding interactions, especially the end-on interactions, they interact synergistically. So that means that the sigma bonding interactions enhance the pi interactions and vice versa, and they stabilize each other, so to say, and leading to an enhanced stability of the metal carbon bond. And that's called the so-called Duncanson model of the carbonyls. So this works the following way. We first create sigma interactions between the electron lone pair here, the carbon and the metal. Okay, so we donate electrons from the carbon into the metal. Okay, so now this enhances the electron density on the metal, and that now facilitates the pi accepting interaction. We can also call them the pi back bonding. Okay, so now part of that electron density gets back donated into the pi star orbital of the carbonyl ligand. Okay, so we have now electron transfer through the pi bonding from the metal to the carbon. Okay, so that now leads to a decrease of the bond order between the carbon and the oxygen, as you can see here. Okay, we add electrons into the interbonding pi star orbitals of the carbonyl, which decreases the bond order. Okay, so with this in mind, we can think of the interactions between the carbonyl ligand and the metal in three ways. Yeah, we can say, well, in the first case, our pi acceptor interactions are relatively weak. Okay, so if this pi back bonding is not very significant, then it would still be most justified to write the metal carbon bond as a single bond. However, if these pi acceptor interactions were stronger, then it would really justify that we write the metal carbon as a double bond and the carbon oxygen bond as a single bond. Okay, but we have to keep in mind that we have an additional set of pi star orbitals available at the carbonyl. We have 2 pi star orbitals available at the carbonyl, so that an additional metal carbon pi bond could form at the expense of another carbon oxygen bond. And that would represent the case of very strong pi acceptor interactions in the carbonyl. So now the next question, of course, would be under which circumstances would we expect weak pi back bonding, weak pi acceptor interactions, intermediate pi acceptor interactions, and strong pi acceptor interactions. And the answer has a lot to do with the charge. So when carbonyls have a high charge, in particular a charge larger than +1, then the pi acceptor interactions are typically weak. Why is that so? That is because in this case, we would have the metal in a formal positive oxidation state. Okay? And when the metal is formally in a higher positive oxidation state, it's less tendency to back donate its electrons to the ligand, because it is already highly positive. However, when we have neutral carbonyls or carbonyls with a weak charge, +1 or -1, then, well, the ability of or the tendency of the metal to back donate electrons into the pi star orbital of the carbonyl ligand increases. And it's of course further increased as the charge is then higher than -1. So when we have metal at the highly negative oxidation state, then of course that metal would have a strong tendency to basically decrease the electron density on itself because of electron repulsion argument, and has a very strong tendency to pi back donate these electrons into the pi star orbital of the carbon. Okay, so now in these general considerations, we can now understand the structure of the carbonates. So first, let's look at the structures of the most simple homoleptic carbonyls. So we are looking here only at carbonyls with a single metal and a certain number of carbonyl ligands around it, whereby the carbonyl would be binding end on to the metal. So again, the 18 electron rule holds, and the carbonyls with the highest stability would have 18 electrons. Okay, so that now determines the number of carbonyl ligands the metal would want to accept. So now we have to distinguish between metals with even electrons and metals with odd electrons. So our carbonyl ligand is a 2-electron donor. So one carbonyl would donate 2 electrons. So when we start out with a metal having an even number of electrons, then an even number plus 2 plus another number times 2 gives another even number. Okay, so it can give 18. But when we start out with an odd number and add 2n electrons, which is always an even number, we always arrive at an odd number. So we arrive never at 18 electrons. Therefore, the structure of the carbonyls with metals having an even number is significantly different than those having an odd number. So when we have metals with an even electron number, then we get simple mononuclear carbonyls of the type MCOX, whereby X is just an integer number. When we have an odd number of electrons, then we get dinuclear complexes. So we add enough carbonyl ligands to a single metal so that we arrive at 17 electrons. And then we dimerize that fragment to make a dinuclear carbonyl, which is then formally surrounded by 18 electrons as well. Okay. The only exception to this is the vanadium hexacarbonyl, which does not dimerize but exists as a radical. The answer for this is that the coordination number to vanadium would become too high if we dimerized it. All right, so we can have still 2 minutes time, so we can briefly go through the homoleptic carbonyls of the 6th group. So this is a group with an even number, so the metals that belong to that group are chromium, molybdenum, and tungsten. So which composition would we expect for stable carbonyls of chromium, molybdenum, and tungsten, where we just need to count the electrons and arrive at 18. So the metal electrons are 6 because we are in the group 6. So the charge is 0. So how many electrons do we have to add? We have to add 12. Okay, 12. And so how many carbonyl ligands do we need? Well, each carbonyl ligand contributes 2 electrons, and then we need 6 ligands. Yeah, 12 over 2, which is equal to 6. So all these metals make hexacarbonyls, which are octahedral. So these are all colorless, crystalline, sublimable solids. All right, I see our time is over, and therefore let's stop at this point.